cats. All right, we're still going to start 4.6. This is graphs of other trigonomic functions. So we're going to go ahead and learn tonight how to graph cosecant, secant, tan, and cotan. Tomorrow in class, I want you to work on that section of your packet. Even if you haven't finished the cosine and sine ones yet, I want us to get some practice while we're all together. And then on Friday, I will check your packets to make sure you've 100% completed those graphs. Then over the weekend sometime, I will go ahead and post, or Monday I'll post a scanned copy of the answers just so you can double check. And tomorrow night we're going to learn about doing things kind of in reverse, where you have a graph and you write the equation, or you have information about a graph and you write the equation, and we'll have a worksheet on Friday in class for that. And then we'll go over everything Monday, and Tuesday we will start our test. All right, so let's talk tonight about graphs of reciprocal functions, which would be our cosecant and our secant. So I want to talk a little bit about that based on what we have done in the past. All right, let's start with our just a table like we had before, our table of values. So we have an x value, which is our theta values, and our basic values, you know, are 0, pi over 2, pi, 3 pi over 2, and 2 pi. Those are our basic values. Let me make sure about it. All right, now let's talk about what cosecant has in common. Cosecant is the reciprocal of sine. So let's talk about what we know about sine first. We know at 0, sine is also 0. We know at pi over 2, our sine value is 1. At pi, our sine value is 0. At 3 pi over 2, our sine value is -1. And at 2 pi, we're back to 0. So if they're reciprocals, then the value of if we took the reciprocal of the sine value, we would get our cosecant value. So our cosecant x values at these particular rotations would be at 0. If sine is 0, the reciprocal of 0 would be undefined. Ooh, that's going to be kind of tricky. The reciprocal of 1 would be 1. The reciprocal of 0, again, is undefined. The reciprocal of -1 would be -1. And again, 0 would be undefined. In the past, when we saw something that was undefined in terms of graphing, we often understood or knew that that meant we would maybe have an asymptote, and that's going to be the case here. So let's take a look at what this sine graph, or this cosecant graph, looks like, and how close it is related to our sine graph. So I'm going to draw our little axis here. And I'm going to label what we had before. We're going to make this our 1, this our -1, and that's at point at 0. We have a point at pi over 2. We have a point at pi. A point at 3 pi over 2. And we have a point at 2 pi. And we can go the other direction. I'll go ahead and put one at -pi over 2. I'm going to have you on your worksheets only graph one period. That way, we talked about that in class, where I can really clearly see your phase shifts and your compressions, but really your phase shifts are the thing that helps me see the best. All right, so this is a parent function, so we don't have to worry about any transformations at this point. The parent function, let's go ahead and graph our parent function for sine, except I want us just to dash in our curve. Just do a dash line or a dotted line in our curve. The amplitude, of course, for a parent function of sine, we know is at 1 and -1. And what do we know about sine? We know sine starts at the axis. And at pi over 2, we would be at the amplitude, back to the axis, bottom of the amplitude, back to the axis. And like I said, let's just dot this in this time. So our dotted line, our dotted sine graph, will look something like this. All right. Now, let's talk about the relationship between sine and cosecant. They are reciprocals of one another. And let's also talk about these undefined terms. So at 0, we're undefined. At pi, we're undefined. And at 2 pi, we're undefined. Notice that those are also the intercepts with the x-axis. Let's see if we can go ahead and highlight in our asymptotes, which would be where we're undefined. So I'm going to use my tools, and I'm going to see if I can pick up a highlighter for us. There's a medium yellow. Well, let's use medium bright green. Okay, so if I do that, we've got an asymptote here. we're going to have another asymptote here, and we're going to have another asymptote here. By the way, since sine has a period of 2 pi, cosecant will also have a period of 2 pi, just to kind of let you know that. Let me go back to our pen. All right, so if we draw in our cosecant graph, it's a reciprocal. A reciprocal is almost like when you flip something. So imagine this dotted line right up here. And what if we flip it? If we flip it, it would flip above that the amplitude, and it would go up like this. Notice it also has asymptotic behavior, meaning it approaches the asymptotes. Because it's undefined, it cannot cross those asymptotes. I could extend those a little bit further. That would help you see it a little bit better. At the bottom down here at 3 pi over 2, it also is going to reflect outward and continue that asymptotic behavior, approaching the asymptotes. And therefore your cosecant graph is the blue graph that you see on this video, and that would be your cosecant graph. I'll tell you a little bit about transformations of that in just a second. Let's go on and take a look at what our secant graph would look like, and I hope that you're guessing by now it's going to have something to do with cosine. So let's talk about a table for that. So we have our x values. Let's go back to our black. All right, so we have our x values, which is our theta, and we know that that is 0, pi over 2, pi, 3 pi over 2, and 2 pi. And now let's talk about secant in relationship to cosine. So we know about cosine x already. We've already done that several times. At 0, cosine is 1. At pi over 2, cosine is 0. At pi, cosine is -1. 3 over pi, 0. 2 pi, back to 1. Now let's talk about in relationship to its reciprocal secant. Again, the reciprocal of 1 would be 1. The reciprocal of 0 would be undefined. Again, we're going to talk about some asymptotes. -1 would be -1. 0 would be undefined. 1 would be 1. All right, let's take a look at what this graph looks like. So we're 0, we're pi over 2, pi, 3 pi over 2, 2 pi, and like I said, we can go the other direction, and sometimes we will. There's no opposition to that. It's just clear when we're starting out to start this way. All right, again, we notice that we're undefined in certain cases, but the first thing I want us to do is I want us just to build our basic cosine graph, but dash it in like we did our sine graph a while ago. All right, so I'm going to say our amplitude and apparent function of a cosine graph is 1 and -1. So I'll put my little dashed lines. And remember, cosine graphs start at the top of the amplitude. So it would start here, go to the axis, bottom of the amplitude, back to the axis, top of the amplitude. Our cosine graph would look something like this. And remember I said to dash it in? Okay, so our cosine graph looks something like that. I kind of messed that up right there. You get the picture, you get the idea. All right. So now let's take a look at where we're undefined. We're undefined at pi over 2. We're undefined at 3 pi over 2. Both are the points that cross, that intersect with the x-axis. So let's draw in our asymptotes. We'll use our highlighter for that again. An asymptote here. I'm going to extend it this time. And we have an asymptote here. Alright, now let's go back and draw in our secant graph. Again, it is our cosecant graph reflected outward or reflected over that amplitude. So if I take this part of this graph right here and I reflect it out, it's going to look something like this. And again, asymptotic behavior because it approaches the asymptote. Down here, it's going to approach the asymptote from both directions. This, of course, is just one period of this graph. And here we're going to approach the asymptote over here. And that's what your your secant graph would look like. Your secant graph would look like. Let's talk about the domain and the range and the period. The domain for this graph, I don't know if we did that before, so it's important, but they're going to be similar. Our domain is going to be all real numbers, except where these asymptotes are. The first asymptote right of 0 is pi over 2. So we can say x cannot equal pi over 2. But it also can't equal 3 pi over 2. And if you move a distance of pi again, it can't equal 5 pi over 2. And that would just continue. So every point from pi over 2, and if you add another pi, you're going to get to an asymptote. So we're going to write it as pi over 2 plus increments of pi. And that you write as n pi. Increments of pi, numbers of pi. Okay, some number of pi. So, 4 of them, 5 of them, however many you add, starting at pi over 2. That's your domain. Your range would go from negative infinity up to, in a parent function at least, up to negative 1. Or it would start at positive 1 and go to positive infinity. And that would be your range. And the period is the same as the cosine graph, which is 2 pi. Which is 2 pi. So those are just some basic information about our graph. Let's go back up and look at the graph before and make sure we put our domain and range in there as well. All right, so our domain, again, would be all numbers starting at 0, so it includes 0, and then pi, 2 pi, 3 pi, so multiples of pi. So we would say x cannot equal, because you can't equal the asymptotes, multiples of pi are increments of pi, and we're going to write that as n pi. Since we start at 0, you don't have to put anything in front of it. The range is the same as the cosine graph. We go from negative infinity to negative 1, or we go from 1 to positive infinity. And the period, again, is the same. It's 2 pi, the same as the sine graph. All right, one last little comment about this before we go to tan and cotan. I want you to notice something where transformations are concerned. If the graph is transformed, in other words, it's shifted, stretched, reflected, etc., then graph these transformations for sine or cosine, then sketch in your cosecant and secant. All right, that's a big helpful hint, and you should be pretty good on cosecant and secant. All right, let's move on to tan and cotan. That'll be it for tonight, and you'll work on these off your packet tomorrow. All right, we're graphing tangent functions and cotangent. And notice I wrote here they were odd functions. Odd functions, if you remember, has origin symmetry. Origin symmetry, and because it's about the origin, we go, our period in tan and cotan graphs is different than our period in cosecant, secant, sine, and cosine. So the period is a big change here, and so I just want you to remember that the period for these graphs is just pi. All right, the period is just pi, so that's for both tan and cotan graphs. All right, so let's go ahead and build our table like we've been doing. I'm going to do one thing that's a little different. We have our x, which is our theta value. And again, we have 0, pi over 2, pi, 3 pi over 2, 2 pi. And we're going to do both tan and cotan on this, and then we'll graph them. One thing I'm going to do is out to the side, I'm going to remind myself what my cosine and my sine values were, my ordered pairs. At 0, it was 1, 0. That's going to help me determine the other. At pi over 2, it was 0, 1. At pi, it was negative 1, 0. At 3 pi over 2, it was 0, negative 1. And at 2 pi, we're, of course, back to 1, 0. That helps me because we know tan is y over x, and cotan is x over y. And so all our x and y values are right there to help us out. So for tan, we have 0 over 1, which would be 0. But if we take the reciprocal of 0, and such as cotan, we would be undefined. We have 1 over 0 for tan, which is undefined, and the reciprocal of undefined is 0. And we continue this pattern. So 0, undefined, undefined, 0, 0, undefined. All right, so it looks like both tan and cotan are going to have asymptotes. We're going to have asymptotes. One other thing I want us to remember is off of our chart something special about tangent, and it would also be true for cotan. At 45 degrees, kind of a key point, or pi over 4, my tan value was 1. Kind of an important thing. The cotan value would also be 1 because the reciprocal of 1 is 1. And that's kind of an important thing when we get ready to graph. All right, so let's take a look at what our tan graph would look like first. Now remember, we're symmetrical with the origin, and we only need to go a period of pi for one rotation for tangent. So we're going to go ahead over here and put negative pi over 2 so we can center around the origin, and positive pi over 2. That distance right there is a distance of pi. That's a distance of pi, and you've got to really understand that. All right, let's take a look at our tan values. Our tan values at are 0 at 0. So we would have a point right here. At pi over 2, we're undefined. Oh, we need some asymptotes. So let's get those. So at pi over 2, we would be undefined. At negative pi over 2, I'm going to tell you that we would also be undefined. Every time you move a total distance of pi, you're going to be undefined again. All right, back to our graph. So at pi, we're at 0. We have that point, and then we're undefined, and it would keep going. Our undefined values would continue. Now, let's take a look at what happens. Halfway between 0 and pi over 2 is pi over 4. Pi over 4, what did we say? At pi over 4, our tan value is 1. So we're going to say this is 1, this is negative 1. So at pi over 4, we're at 1. Now, let's take a look at our unit circle right here. Negative pi over 4, which would be right here, puts me in the fourth quadrant. And remember, all surfers to California. And in the fourth quadrant, tangent would be negative. So it's going to be negative 1. So you're going to come down here to negative 1 and put a point. And that's going to build our graph. Again, they're going to move toward the asymptotes without bound or no limit, and with no limit. And so we're going to come down here, go through this point, go through our point down here, and graph. This becomes a point of inflection. And now let's take a look at, and this was our tan graph. Let's take a look at our cotan graph. It's going to be really similar. We're almost done. All right. Cotan is going to be a little different in terms of where we place it along the grid in terms of our parent graph. So cotan is going, let's go ahead and put our values here. Pi over 2, pi, 3 pi over 2, oops, and 2 pi, and then we have negative pi over 2. All right, so let's take a look at where our undefined values are for cotan. For cotan, we're actually undefined at 0 and undefined at pi. And remember, again, the period is going to be a distance of pi. If we go from 0 to pi, that right here is a distance of pi. So let's go ahead and highlight in our asymptotes. So 0 would be an asymptote, and pi would be an asymptote, and 2 pi and 3 pi, and etc. All right, let's take a look at what else we have. We know that at pi over 2 we're 0, so we have a point there. We also know that we're going to have a point at pi over 4 and, oh sorry, this is pi over 4. This would be 3 pi over 4. So let's talk about that. At pi over 4, the reciprocal of tangent, which would cotangent, is 1, so we would still be at 1, and we'll just mark that as our 1 right there. We know we're at 0, and at 3 pi over 4, it's going to be 1, but is it positive or negative? 3 pi over 4 puts us in the second quadrant, and in the second quadrant, tan would be negative, so it would be negative 1 down here. Looks a lot like cotan would be negative because it's in that quadrant. Cotan and tan are going to look a lot alike, just kind of flip-flopped. So we're going to be asymptotic behavior toward the asymptote on the left, come through, do that very good, and then curve and do our asymptotic behavior on the right. Sorry, my pen's not working very good, but you get the picture. Okay, so these two graphs look a lot alike, just kind of flip-flopped back and forth. I think that's really it. Again, when we talk about stretching or compressing, we'll use this 1 as our marker, and we'll talk about that a little bit more when we get to graphing. So we'll practice these tomorrow, and then we'll work on writing equations from graphs on Friday and tomorrow night with a video. Hope you have a good evening, and go Bearcats!